So now we're going to take a look at vertical stretching and shrinking. So f of x equals 3x squared. We know so that's the basic function x squared, which would look like this. Again, this time my window is set from -5 to 5 for the x and -5 to 5 for the y. And that's just the graph of regular x squared. So let's go ahead and draw in 3x squared. So to turn on 3x squared, it'll draw that right in there with the regular x squared, and it is vertically stretched, so it gets taller at each point. It's easy to mistake that for also being a horizontal shrink, which you'll see later. But this one, since the 3 is right there, it is a vertical stretch. Each point is just up higher. Now for part B, 1/3 x squared, I'll turn off part A. We'll just graph the 1/3 x squared and the basic x squared function. This should be a vertical shrink, so it's going to appear shorter and, because of that, a little bit wider. And that's vertical stretching and shrinking. For this example, we're going to combine several different things. So this is f of x equals 1 minus 2 parentheses x minus 3 squared. So the basic function is the x squared. This minus 3 is going to shift it to the right 3. The 1, that's like being added on at the end, so that's going to shift it up 1. The negative out in front of the x is going to flip it upside down. And also there's a 2 out in front, which is going to stretch it vertically by a factor of 2. So there's a lot of information. We'll just make a sketch of it. It shifts right 3 and up 1. So there's our vertex. It is also going to be upside down. The arrow's pointing down because of the negative. And it's going to be taller, which will make it appear a little bit skinnier by a factor of 2. Something like that. For a more accurate graph, you could plug it into your calculator. You can see essentially the same thing. It shifted to the right 3, up 1, opened down, and it's hard to see the vertical stretch because there's nothing to compare it to, but it's there. Here's an example on horizontal stretching and shrinking. This time we're not given the actual function, just the graph, and we need to determine by looking at what they do, does it stretch or shrink? So this time there's a 2 in front of the x, and if you recall, that is going to, anytime it's with the x, it is going to do the opposite. So it's not actually a stretch, it is a shrink by a factor of 2. So instead of, let's say horizontal shrink by a factor of 2. So instead of touching all of the points at the x-axis at 1 and 2 and 3, it's now going to do that at 1/2 intervals. It does not change the height of the graph, just shrinks it horizontally. So rather than touching at 1, it's going to touch at all the halves. So it has to do a full peak and back at each half value. And the same thing on the negative x-axis. Now when you multiply by 1/2 in front of the x, that is going to stretch it horizontally. So it will not change our peak value of 1, but it will change where it touches on the x-axis each time. So now instead of touching at 1, 2, and 3, it's only going to stretch by a factor of 2, so it will touch at 2 and 4 if we extended it. And the same thing on the negative x-axis. Even in odd functions, this will seem familiar because it's very similar to what we did to test for symmetry. If a function is even, plugging in a negative x doesn't change. F of negative x is the same as f of x, which would mean it also has symmetry with respect to the x-axis. An odd function, when you plug in negative x, the negative gets pulled out to the front. So f of negative x equals negative f of x, which would also mean that it's symmetric with respect to the origin, or a rotational symmetry. So all you need to do is plug in negative x and see what you get, basically. So to test if a function is even or odd, we're going to plug in negative x. And make sure you use parentheses, because that's the only real place you can mess up with this. So when you do that, since it's negative x to the 5th, that negative will stay. And then plus a negative x, it's the same as minus x. Since all the signs changed from positive to negative, all the signs changed means it's f of negative x equals negative f of x, which means it is an odd function. We're going to do the same thing for part B. We're going to plug in negative x in place of x. Now, since this is to the 4th power, negative times negative times negative times a negative will get us positive. So this will simplify to positive. You're subtracting positive x to the 4th, which is the same as the original function. Since it's the same as the original, nothing changed. That is an even function. And last, h of x, we're going to plug in negative x. So that becomes negative 2x the negative x squared becomes positive x, so it's minus positive x squared. So one sign changed, the 2x changed to a negative 2x, but the second sign did not change, so that means it's neither. So if all the signs change, it's odd. If none of the signs change, it's even. And if you get a mixture of both, it's neither odd nor even. Also, you can notice x to the fifth and x to the first. Those are both odd exponents, and it's an odd function. We have a constant, which means it has an x to the 0. 0 is an even number. And x to the fourth. 0 and 4 are both even powers of x, and it is an even function. And here we have a mixture. We have an exponent of 1 and an exponent of 2. We have one odd, one even, and it is neither an odd nor even function. So there's a little shortcut that you can notice. If all the exponents are odd, it's an odd function. If all the exponents are even, it's an even function. If you have a mix, it's neither.